This is the lectures. Hello and welcome. This is lecture on thermodynamics. We are going to provide, what is this? Okay. This is nice. Okay, so welcome everyone. This is a very brief introduction of thermodynamics. I will continue all the classes if this will be my first video that I will be uploading on YouTube, so be patient. And if you like the classes, if you like these notes, these are again PW notes. This is a physics wala note. It is a coaching institution. For those who don't know, it's a coaching institution known as physics wala. So please be very oh my god. Hello, good morning. Hello everyone, welcome to my YouTube channel. This is a brief revision of thermodynamics. So the idea behind this lecture or this video is that I want to go briefly around all the topics that are there in thermodynamics, and this is very useful for GATE, also for your university examinations. So you can follow this. This is basic thermodynamics first of all, in which we will deal with macroscopic viewpoints. We will talk about viewpoints over here, but you can also take screenshot. Like this is like one page, so I'll be explaining like this. Okay, so this is our first page. You can take second screenshot over here, you can take third screenshot over here, you can take fourth screenshot over here. So you will like this, you will get the whole page. Okay, so without wasting any time, because the whole purpose of this is to provide RAM in as much information as I can in like 5-10 minutes, 15 minutes max. Okay, so first lecture 15 minutes, let's go. Okay, thermodynamics. So the name suggests therm means like heat, and dynamics is like flow of heat. So we'll not discuss that right now. What we will discuss is what is the engineering wise, what is the definition which is very fit for thermodynamics. So this is that definition. The definition is that the main aim of thermodynamics is to convert non-organized form of energy, heat, into organized form of energy. Now, what is organized form of energy? What is non-organized form of energy? See, that is defined as the viewport you are looking in. But heat is a form of energy which is very diverse. Heat is very random. Heat is very we can also say heat is not very concentrated form of energy. Concentrated form of energy is work. Like if there is a shaft, then the energy will flow on the shaft. Okay, it will give the torque along the shaft line. Okay, but heat, if you are like transferring heat through a tube, heat will radiate out of that tube. Okay, I don't know how you imagine radiation, but heat will radiate out of that tube very much. Okay, and also it will be actively be cooled by air, and then radiation will be further, so heat will be lost. So heat is not very concentrated. So that is a non-organized form of energy. Okay, heat, which is organized form of energy. Work, here it is work. Also be electricity, it can also be electricity. Let's move further. Thermodynamics is a branch of science which deals with heat and work interaction. Thermodynamics is a branch of science which deals with the heat and work interaction. So thermodynamics works with heat and work interaction. Thermodynamics is a branch of science which deals with the heat and work interaction, and it affects on the properties of the system. Okay, so thermodynamics is a branch of science. Now it is a branch of science which deals with the heat and work interactions, and it affects the properties of the system. It affects the properties or effects on the properties of the system. Okay, heat and work interaction. Thermodynamics is studying dealing with heat and work interaction, and also the effects on the properties of the system. The heat and work interaction, what are the heat and work of that body interactions are, what are the effects they are posing on the properties of the system. That is also dealt with in thermodynamics. Okay, so first of all, what is it dealing with? Heat and work interactions, and also the effect on the properties of that system. Okay, laws are the statement which are universally truth but can't be proved mathematically. Laws are came into existence by common experience, the common experience, or we can say experimenting. Okay, laws are statement which are universally true. Okay, you cannot deny that, you cannot neglect, or you cannot negate that a law. Okay, that is a law, like you cannot negate the law. Okay, a law is universally true statement. How it is only a statement? Because I have done some experiment, and again, through and through, time and time, the result was only one, so I made a law of it. Okay, and you cannot negate that, because you have no proof. You have to run your own experiment, and you have to negate my law scientifically, but mathematically there is no proof of that. So that is a law or the statement. Now from that statement you can make a mathematical proof. Okay, from that statement you can write it in mathematical terms, but originally there is no mathematical proof. Like the law did not what we can say, the law did not give, the mathematics did not give birth, like simple logic, human logic did not give birth to the laws. Laws are something that we understood by the behavior of physically experimenting, or physically doing experiments, and then we convert it into mathematical language. So that can be a law, but law are the statement which are universally true and can't be proved mathematically. No, mathematically there is no proof. And also they came into existence by common experience. I have done a experiment, then I have gave that knowledge to you, then you did the same experiment to check, and the results were same. So that is a law. Okay, so speciality of thermodynamics. So what is the speciality of thermodynamics? Interview may ask. So most importantly, thermodynamics tells us things that are not possible. Thermodynamics tells us the thing that are not possible. Most importantly, this is the main major role of thermodynamics, that it tells you the things that are not possible. Okay, according to second law of thermodynamics, no heat engine can give 100% efficiency. So this is the example that no heat engine can give 100% efficiency, because there will be a heat loss, there will be some degenerative factor to heat. And heat is also, first of all, heat is also very low grade energy, or you can say heat is very non-organized form of energy. So non-organized form of energy, you cannot concentrate it enough to make 100% efficient heat engine. So here it is, according to second law of thermodynamics, no heat engine can give 100% efficiency. Applications of thermodynamics. Importance of thermodynamics. There is one property which distinguish thermodynamics from other sciences, that is temperature, and everything have certain temperature. So everything come into the consideration of thermodynamics. Importance of thermodynamics. There is one property which distinguish thermodynamics from other sciences, that is temperature, and everything have certain temperature. So everything come into consideration of thermodynamics. What is the importance of thermodynamics? So you can say this: there is one property which distinguish thermodynamics from other sciences, that is temperature. Because temperature is the word that derived, or that came from thermodynamics itself. First of all, we studied thermodynamics, and then we made up these terms known as temperature and so on. So yeah, have certain temperatures. So everything came into the consideration of thermodynamics. Everything came into the consideration of thermodynamics. Then everything have certain temperature, so everything came into the consideration of thermodynamics. Before undertaking an expensive project, an engineer must know the answer to following questions. First is the proposed chemical reaction. The proposed chemical reaction might be visible. Okay. Before undertaking an expensive project, an engineer must know the answer of following question. Is the proposed chemical reaction physical process possible? Is the proposed chemical reaction physical process possible? If possible, then up to what extent? What factors will govern the process? How much energy is required? What will be the max efficiency? Thermodynamics provide answer to all questions. Okay, so these kind of questions thermodynamics provide answer to. Let's go further. Okay, how to study thermodynamics? There are mainly two viewpoint of thermodynamics. Well, what is microscopic and macroscopic? Microscopic is basically called statistical thermodynamics. We will not study statistical thermodynamics right now. Useful for low density gases or low density, systems with low density. Macroscopic viewpoint is classical thermodynamics. This is our subject. So macroscopic viewpoint is very high density, you can say. Microscopic viewpoint, matter is composed of myriads of, myriad means millions of molecules. In microscopic approach, the behavior of individual molecule is taken into consideration. Okay, in microscopic approach, what we are doing, we are taking into consideration every individual molecule of the system. The overall behavior is described by summing up the behavior of each molecule. Now the overall behavior is described by summing up behavior of each molecule. We are summing up the behavior of each molecule and we are averaging that thing. So we are averaging the sum that is derived by summing up all the molecules. So then we are coming into taking an there is an answer. Okay, only useful for low density. Now again, only useful low density. Why we are talking this again and again? Low density, we'll just prove it. Okay, it is also known as statistical thermodynamics. As we have discussed earlier, statistical thermodynamics is not in our syllabus. Individual behavior of molecules is considered. Macroscopic viewpoint, on the other hand, in macroscopic we fix our attention to certain quantity of matter. Now we first of all, there is a system, then we fix a smaller certain quantity in the system. We fix our attention to it of without going into the event occurring at the molecular level. Then we are not going into the event which is occurring on a molecular level. We are just focusing on a certain part of a system that we have even out. Okay. Average behavior of the molecule are taken into consideration. Now average behavior of the molecule is taken into consideration. This approach is known as classical thermodynamics. What you are doing, taking a system, you are taking a small part of the system. Now you are not collecting the data from every molecule in the system. What you are focusing on is a small part of system, and then you are focusing on their events, like what is happening on this small part molecular level. Okay, is known as classical thermodynamics. In macroscopic viewpoint, we will try to establish the relation between measurable and non-measurable properties. In macroscopic viewpoint, we will try to establish the relationship between measurable and non-measurable properties. Measurable properties: pressure, temperature and volume. Okay, in macroscopic viewpoint, we will try to establish the relationship between measurable and non-measurable properties. Measurable properties are pressure, temperature and volume. Non-measurable is entropy, enthalpy and internal energy. Now we will discuss further why we are taking that measurable and non-measurable. See, measurable is measurable, pressure is measurable, temperature is measurable, volume is measurable. Now entropy you cannot measure, enthalpy you cannot measure, internal energy there is no means to measure. Okay, concept of continuum. Now, this is very you can say very important bit. Concept of continuum. Okay, so there is a system. What you are doing, you are taking a small part out of it, and dv equals to dm is dv is the small volume and dm is the small mass. Okay, this is the graph of concept of continuum. We'll discuss this, it further. Now what concept of continuum says is it gives the criteria to apply macroscopic viewpoint continuum homogeneous matter with no holes. Okay, concept of continuum basically gives us the criteria to apply macroscopic viewpoint. Concept of continuum basically gives the criteria to apply macroscopic viewpoint. Okay, in macroscopic viewpoint we always concerned with the volume which are very large compared to molecular dimensions. Even a very small volume of the system is assumed to contain large number of molecules so that the statistical averaging is meaningful and matter can be treated as continuous. It gives minimum volume, so the system should be continuous and averaging is meaningful. For solid and liquid it always holds good, but for gases and low pressure it is not so true, as the distance between molecules are more. We can check whether concept of continuum is valid or not from Knudsen number, which is a ratio of mean free path. Mean free path is the path a molecule distance a molecule cover between two successive collisions to the characteristic dimension. Now what is characteristic dimension? Characteristic dimension is nothing but we have to divide. See, Knudsen number do not have any dimension. It's a dimensional quantity. So mean free path is L, like it's a length. Okay, now characteristic dimension is volume by surface area. So you can see the characteristic dimension unit is also L. So L by L is unitless. So you can characteristic dimension, you can remember it easier, like volume is L cube and surface area is L square. So you can, okay, so this is your system mean free path. So this is a system which has low volume, which has low density. This is a high density system. Okay, mean free path is large, not in continuum. So this is mean free path is large, not in continuum. Mean free path is small, it is in continuum. How it is in continuum? You can see mean free path is large. If the mean free path is large, then this ratio will come, this division will come bigger. Okay, and there is certain limit on, let's say, number to be into the continuum. Now why we are not applying continuum in low densities? Because see, if we take a small area or small system and we focus our attention to it, we will be not able to average it out. See, only 2 or 3 molecule will come into our consideration, and that too also if we are concentrating it, there is a much probability that one molecule comes in or 2 molecules goes out. So it's an unstable kind of thing. Okay, averaging is not possible. Like you cannot apply macroscopic viewpoint. It will give wrong answers only. This is, on the other hand, this is a dense system. It will give right answers because mean free path will be small, characteristic dimension will be like equal. Then you will have a Knudsen number which is less than 0.01. Okay, so this graph is also taking us to that only. If there is like if the density is like dm by dt is more, then concept of continuum can be applied. If the density is low, concept of continuum cannot be applied. So this is the domain of macroscopic viewpoint, this is the domain of continuum. Okay, this is the domain of microscopic viewpoint, this one. Okay, because then you have to, density is very unstable. Okay, the molecules are going haywire over here. These are densely packed molecules, so you can apply continuum here. You cannot apply continuum here. You have to apply statistical techniques, statistical thermodynamics domain, you can also say. This is our classical thermodynamic domain. Okay, in any system. Mean free path is the average distance traveled by the molecule between 2 successive collisions. Okay, Thermodynamic system surrounding and boundaries. Now, quantity of matter, region, space. Everybody knows what is. Everybody like gives different examples, different definition of thermodynamic system. So, thermodynamic system, you have to only remember two key points: quantity of matter and region, space. And you have to say, if anybody asks you what is thermodynamic system is defined as a quantity of matter or region is space where our study is focused. Quantity of matter and region space are the utmost important keywords that you have to say. Okay, system, quantity of matter or region, space, thermodynamic. This is the thermodynamic boundary. This is the system, which is the quantity of matter and region, space. This is surrounding. Okay, I think this is the whole box is universe. Everything external to the system is known as surrounding. Everything external to the system. What is the system? It is defined as quantity of matter or region, space, which is study is focused. The system is separated from its surrounding by its boundary. ठीक है, system is separated from its surrounding by its boundary. Okay, system जो है वो surrounding it is separated by its surrounding, by its boundary from the surrounding. Thermodynamic boundary, no imaginary boundary. See, the door is closed, so this is, see, although yes, a disclaimer, this is PW notes. PW means physics wala notes, and these are the running class notes, so I've made them and I'm presenting them in front of you. So I don't take any ownership of these notes. I'm just merely trying to spread the knowledge how much I can. Okay, so no mass transfer, all bodies are real, closed system, quantity of matter, fixed mass, control mass system. We can also say control mass system. We can also say it is a closed system. Okay, all boundaries are real, no mass transfer is happening over here because the door is closed. Now the door is open, you have two region. Now this is the region in space. This is the region in space. Okay, quantity of matter or region in space. So you have to imagine it. You have to go to an imaginary boundary over here. You have to imagine a boundary over here, which is known as imaginary boundary. But you can see the mass transfer is possible. Okay, region is space, control volume. Mass transfer also take place. Heat and work transfer. Okay, work and heat transfer is possible, no mass transfer is possible. In closed system, open system, everything is possible. Only mass transfer is not possible in closed system. Imaginary boundaries, if you want to work from a closed system, I think this is here. If you want to work from a closed system, minimum one boundary should be movable. Now I'm not saying the one boundary should be open, but movable, like a piston, right? Real boundary is a boundary which do not allow mass transfer through it. Okay, real boundary is a boundary which do not allow mass transfer through it. Thermodynamic boundary, real boundary, fixed or moving. Imaginary boundary, all are fixed. Real boundary, gas is equals to mass is constant, volume is constant. Let's keep it to that. We will discuss more in more videos. So thank you for watching this video, this introduction to thermodynamic. What we have studied, we have defined thermodynamic, speciality of thermodynamic, application of thermodynamics, what is the application, what it tells. Then we have how to study microscopic, macroscopic, statistical and classical. Macroscopic viewpoint we have defined, microscopic viewpoint we have defined, and concept of continuum. This is very important topic, concept of continuum. You have to understand what is concept of continuum, how to apply Knudsen number, and how to test that if concept of continuum will hold or not. Okay, for low density there is no concept of continuum. For high densities, okay, classical mechanics, classical thermodynamics also we can say. Thermodynamic system, if somebody asks what is thermodynamic system, you have to tell it is quantity of matter, region, space. You have to include these two words. This is very important. Okay, and yes, imaginary boundary. Okay, to get work from closed system, we also just have introduction to imaginary and non-imaginary boundaries. Then closed system and open system. In open system you have to imagine imaginary boundary, and in closed system there is no, there's all boundaries are real. Okay, to get to work from enclosed system. Now closed system, minimum one boundary would be moving, should be moving. Okay, thank you.